Welcome back, folks. We're looking at performing DC analysis around a BJT in a circuit. Okay, so we've figured out that the volt-amp characteristics are nonlinear, and we have to find some way to deal with these nonlinearities. So using MATLAB would work. Load lines are okay in certain instances, but they're very limited in their use. More often than not, what we choose to do is make some linear assumptions, and we use those linear assumptions to perform either mesh or nodal analysis. Let's take a look at how we do that. All right, so when we start out doing DC analysis, we're going to assume that we're in the active region. Okay, that's the first of 4 regions, 3 of which are kind of the most important. So we always assume active to begin with, and we start out by saying the base emitter voltage is 0.7 volts, and that's not unlike the assumption that we make for the diode, and it makes sense. They're both PN junctions. Okay, so we're going to assume that voltage is 0.7 volts. Again, this is silicon that we're using to make these transistors. Okay, the next assumption that we make really has to do with the nature of the BJT, and this is the part that ends up amplifying things. We have the collector current and the base current, and they're related by a value beta, and beta is the current gain of the BJT, right? So let's see here, right? So that is the current gain beta. And that's a parameter. You can look that up in a data sheet, no problem. It is very thermally unstable, but we'll deal with that in coming videos. Okay, so you can find a reasonable value for beta in a data sheet. And all we do is take the current flowing into the base and we multiply it by beta to get the current flowing into the collector. So we can make that assumption. That's a nice linear assumption. Okay, and then the last assumption we can make is essentially a KCL. We're saying the current flowing into the base and collector add up to be the current in the emitter. Okay, so if we're looking down here at our schematic symbol, these currents flow in, that current flows out. So you could rearrange that to look like most of the KCLs we write, but it's a KCL, right? Bring that over and it's negative, and we get 0 on that side, and it's negative because it's leaving. Okay, so that's really just a KCL for the entire transistor. Now, you can work with these assumptions just like that, and you can leave the schematic drawn with an NPN without a problem. But if you'd like to, and if it helps you, and I'm going to do it a good number of times in this class, you can make those same assumptions. You can kind of restate them in the form of an equivalent circuit, and this is the DC equivalent circuit. Okay, we're going to have a couple different equivalent circuits for a BJT. This one is for the DC equivalent circuit. Okay, and we can see that the base emitter junction is connected by this diode, and we're making the assumption that that's 0.7 volts. Okay, so that's our first assumption from up above here. The other thing that's going on is we have a current gain, beta. Okay, so the current flowing into the collector is equal to beta times the current flowing into the base. And we can state that assumption by using this dependent supply. Okay, so we can get that diamond up there, and this current flowing down is dependent on this current over here. And that's what's actually going on in a BJT. Okay, finally, with this KCL, we can do that at this node here. And these currents tend to stay in the directions that I have drawn here by convention. Okay, so let's draw those over here. Oh, not IE, IC. And they match the current directions over here. Okay, so if we write the KCL here, we can say IB goes in, IC goes in, IE goes out, and you can rearrange that to get that third assumption. Okay, so if we're more comfortable with the assumptions in this form, we get to just pull this out of the circuit, redraw the whole circuit, pull that NPN out of the circuit, and redraw it as this DC equivalent circuit. So let's practice this. Let's get a simple circuit going and see what all this means. Okay, so let's see, real simple. As simple as we can get to start ourselves off here. I promise you we will get more complex. I want you to be able to solve any of these. Okay, so we ground that. And what do I have for values? 86 kilo ohms and 150 ohms over here. All right, and let's tie those together and get ourselves a voltage supply. This is plus 5 volts. All right, and since this is the only resistor connected to the base, real frequently we'll call that RB. And since this is the only resistor connected to the collector, we'll call this RC. If we had one down here in the emitter, we'd call it RE, but we don't. Let's say that we have a beta value of 200. All right. Looks like that. And that's our circuit. We want to find what's called the Q point. Okay, there are no other supplies disturbing this circuit. So we call it the Q point, which is short for quiescent. It just means all the other supplies are quiet. Okay, there's no audio input. There's no sinusoid disturbing this circuit anywhere. We have pure DC. Okay, so it should be nice and quiet. Okay, so that Q point is a point on our VI characteristic that we had in the last video. Okay, and that means it's going to be defined by 3 values. It's a point on that curve. Let's see, a point on the VI characteristic. So we got to think about what the axes were. Characteristic, curve. Okay, one of the axes was IB, right? That was the one giving us all the steps in the curve. The other one was VCE. And then finally the output, the vertical axis, was IC. So if we want to find the Q point, these are the 3 values that define our Q point for this transistor. Once we have that, we can kind of figure out what's going on. But we'd like to do nodal to find these values. Because if we use nodal on this circuit, then we can go find any other value we would like in the circuit. Okay, so that's a good quote, in my opinion, and said by a very wise man in the field of circuit analysis. And you know, once you find the node voltages, you can find any value you like in the circuit. So I want you to remember that, and remember which wise man said that. Okay, really, really sharp guy. Okay, good looking too. Anyhow, so we want to do nodal analysis. Okay, and the way we can do that right now is by making the equivalent circuit. So we got to think about, we got to do this real careful. We got to say, what are our nodes, our non-reference nodes? I'm going to call that B since it's the base. I'm going to call this C since it's the collector. The emitter's grounded, so it's not a non-reference node. And if I have B and C, I might as well call this A, right? All right, so we got to redraw that circuit using the equivalent circuit. All right, and I want you to remember that there's a voltage supply out here too. When you get one of these bubbles, I want you to think about it as a voltage supply connected to ground, just like that. Okay, so I'm going to redraw this, and I'm going to start by saying, well, that's a 5-volt voltage supply. I'm going to start by copying that 5-volt voltage supply down here. Okay, just off the screen. I'll scroll up in a second here. All right, and there's probably cleaner ways to draw this, but I want it to somewhat match what's going on. And this is our RB, 86K, comes down here and connects to that diode, right? The diode comes out here, and here's ground, just like this, all the way over to ground. I gotta scroll up a skosh more, and then the 150 was over here. Okay, and we connected to our collector, and on the collector we had that dependent supply. Okay, so it's big and ugly, and that's fine. We can work with it. We gotta find our non-reference node. So if we're working off the other schematic, the 5 volt was A, right? This was B, and this was C here. So we want to find those voltages, and then we want to find them. We want to use them to go find the Q point. All right. So this is 0.7 volts. That was one of our assumptions, right? And there's IB, and this is going to be beta. Beta was 200 times IB. All right, this is our circuit. Now we just do circuit analysis on this, and you can do it any way you want. I'm suggesting you should maybe think about using nodal, and you'll be a lot happier in the long run. And we'll use MATLAB to do the rest of it. So I've got three non-reference nodes. So that means I got 3 unknowns, and that means I'm going to need 3 equations. Okay, so let's write some equations over here. So we got VA equals 5 volts. And that's from the KVL here. Okay, down here we see VB on the positive side and ground on the negative side. So we can say VB equals 0.7 volts. Hey, we're cruising. Okay, 5 volts, 0.7 volts. We need VC. And in order to get VC, we're going to have to write a KCL. Okay, and let's see, where can I write this KCL? I can't write it for A because it's connected to 5 volts. I can't write it for B because it's connected to this 0.7 volts. So I'm going to have to write it for C. Okay, so let's write a KCL at node C. And let's see, that's going to be VA minus VC over 150. And then minus 200 IB. And that's equal to 0. Now that's okay for starters, but IB is not one of the unknowns, so we got to relate IB to our node voltages, and we can really think of the KCL here. Is it worth writing the KCL? Right, IB is leaving B, and we have plus VA minus VB over 86K. Okay, and that's equal to 0, but we really want to solve for IB, so if we bring IB over to the other side, right, it becomes positive, and we have that expression for IB, so I can even bring IB over there. Say IB is equal to that. Okay, so we get to plug that in. Take that and plug it in right there. And we get VA, is this going to be behind my head? I'll come over here. VA minus VB, VA minus VC, excuse me, over 150 minus 200 times VA minus VB over 86K. Okay, and that's equal to 0. And that's our third equation. All right, so let's see, we got one equation here. We got one equation here. Those are easy. This one's a bit uglier, but not undoable. All right, so let's do that in MATLAB real quick, and let's find our node voltages. And then I'll teach you how to check your assumptions. I'll do that in another video because I don't want to put you to sleep yet. Do I have MATLAB open? Yes, I do. What kind of shenanigans was I getting myself into? All right, clear all, close all. I got to zoom out. I think you've seen this enough. Okay, clear all, close all, and there we go. All right, and let's set up our symbolic variables, VA, VB, and VC. And let's get our first equation is VA equals 5. Let me get V1, VA. There we go. Second equation is VB equals 0.7. Those are nice and easy. Third equation is KCL with a few terms. So we get VA minus VC over 150 minus 200 times VA minus VB divided by 86K. Okay, that's equal to 0. So not too different, right? Once we have these assumptions in place, we just do the circuit analysis the way we've been doing it. It's not magic, folks. You've shown me that you can do nodal analysis already, and I believe you can still do it just with the BJT. Okay, so we're going to solve it and put it in SOL, and that should give us, where am I going to put this? Wrong class, 323 videos. That's going to be here for now. What do I want to call it? I want to call it the same thing as the file over here. CT323 BJT DC. That's going to be 02. Okay, that way you have some shot at lining up what script I used in which of the videos. Okay, so let's go ahead and run that. Hopefully we have a solution. We do have a solution. Okay, so if we wanted to figure out what was going on there, we could say, show me what VA is, and it's 5. Well, it better be, right? And VB is 0.7, also known as 7/10, and VC is 7/2, which is 3.5, right? Okay, so we have those values, and we can enter those here. So let's see, VA equals 5, no kidding. VB equals 0.7. Those can get more complicated as the circuits get more complicated, and they will. And VC is 3.5 volts. Okay, so those are our node voltages, assuming that we're in the active region. We need to use those node voltages to go figure out what's going on and check that assumption. Is it actually in the active region? And there's two ways we can do that. So I'm going to leave that to another video, but we're going to pick up right here with VA equals 5, VB equals 0.7, and VC equals 3.5. All right, stay tuned and good luck.